And I think the main problem was that there have been, in the past, people have tried aquaculture here in Sisal, and they have failed. And these aquacultures, they were on an industrial scale. On the bottom right, you see the cages that have been washed up on the beach because the anchor didn't hold, and other problems. Because there's kind of interesting environmental conditions. As you can see here, Storm Milton, I think everyone can remember that storm. But it's not uncommon, those hurricanes and those strong weathers. So yeah, you need to kind of design the cages for that. Also a reason why the project failed is because the people here feel the local demands were not heard. Their interests and the things they found important were not taken into account because these cages were on an industrial scale, and like it did not connect with the community. This resulted in skepticism towards the adoption of the cages. And this project is part of a larger project, so multiple years. So we're hoping to kind of contribute our fair share to this project, and hopefully the successful implementation of aquacultures in Sisal. So we have the problem, and now it's like, okay, how are you going to tackle this problem? And I would like to refer to a quote of my dear friend Steve Jobs, and he said, Picasso had a saying, "Good artists copy, great artists steal." And what I'm trying to say is that, okay, we came here and we were like, we need cages. We didn't know anything about cages, but are there not an example of cages in the area? So we ended up in Celestun. Celestun is a fishing port nearby. And we chose this location because it has a similar geographical location on the same continent shelf. It has already proven to be economically viable for a small fishing community. However, the environmental conditions are different. The depths are different, and the currents and waves and so on, which will be elaborated on further. And their cage is found to be too far offshore for the fishermen, which it increases fuel costs and so on. But because of the fishing refugee area, they could not put it any closer to the shore. Also, it has shown occasional failures. The Celestun setup is 3 cages, and in the bottom right, when we visited, it's 2 cages. So one of the cages failed and broke actually due to the environmental conditions. So what we did is we took the Celestun cages as a basis, and we did some measurements and took photos of how the construction actually, how it was constructed. So yeah, that formed our basis for this project. Then we defined our main research question based on this. Our main research objective is providing recommendations for the design and implementation of an offshore aquaculture in Sisal. And these recommendations are for a long-term success. And we divided them into 3 sub-objectives. Determine the best offshore distance for the aquaculture location in Sisal. Analyze the environmental forcing conditions in the waters off the coast of Sisal. And provide design recommendations based on the determined and analysis environmental conditions of Sisal. This is our agenda. So our methodology, like I said, we divided our project into 3 parts. The first part will consist of a site analysis and determination. Jetse will talk about that. Then we've done a data analysis, data collection and analysis. Chris will talk to you about that. And then part 3, Tom and Martijn will talk about the design concept and procedure, and some simulations, and eventually an anchor design procedure. This all to provide recommendations for the aquacultures in design in order to ensure a long-term success. I'll give the word to Jetse now.
Yeah, thank you, Sebas, for that wonderful introduction.
Okay, as Sebas explained, we first had to determine where we want actually to place the cages. So how we did that, was that we chose certain distances offshore from Sisal, and the distance ranged from 2 till 20 kilometers offshore. And this range was based on academic reviews and talk with experts. So to see what influences those locations and what factors are important for those locations, we conducted some interviews. And these interviews helped us to give interest, to set a context, and to see the perceptions from the parties involved. So we interviewed fishermen, as you can see here. We interviewed a fisherman from Celestun. Also, we visited at the beginning of our project a meeting between the fishermen in Celestun and the fishermen in Sisal. And this was about exchanging knowledge of the fishing cages in Celestun. Also, I think you all know him. We also interviewed and talked a lot to our dear friend Carlos over there. And again, the main reason was to identify the different criteria that are influenced by those distances. And what came out of these interviews was that the criteria actually, you can divide them in three main subjects, which are the local criteria, the environmental criteria, and the structural criteria. And our job was to find a meeting point. We call it the solution space of all those criteria. So we want to see an optimum of all those criteria, because every criteria has a different favor to a distance. For example, fuel consumption wants to be a distance closer to shore, because then there's less fuel costs. And what we did was we gave every criteria a score from 1 to 5. 5 means that it performs really well on that distance, and 1 means that it performs really bad. So you can see here on the right-hand side, light blue represents fuel consumption, and at 2 kilometers, it's get a quite a good score, namely 5, which means that it is very good at that distance. At the same time, we show water flow through cage, and you can see that at 2 kilometer distance, this criterion performs really bad and scores therefore a 1. And as the distance increases, the score also increases. So what conclusion we have to draw from this figure is that not all criterion are considered good at the same distance. And another thing we draw from the interviews we did was that the parties involved, so the fishermen, but also the experts, didn't weight the criteria all at the same. So, for example, fishermen really favor fuel consumption above accessibility of the tourism tours. So we give every criteria a weight, and this weight represents the importance of that criterion. So, for example, fuel consumption is 2 times more, contributes 2 times more in the long-term success of the fishing cages in Sisal than accessibility of the tourism tours. With this information, so with the weights and with the different scores we gave to each criteria, we conducted a multi-criteria analysis, as you can see here. So the scores were added up for each distance, resulting in this figure. And as you can see, 8 kilometers gives the highest amount of score, which is 37. So we can conclude that this distance is the most ideal for the long-term success of the fishing cages in Sisal. However, there is one big problem with MCA analysis, and that is that a lot of consumptions are being made during the process, and there are also a lot of uncertainties. So a way to tackle this is to perform a sensitivity analysis. And with the sensitivity analysis, the goal is to check the robustness of the MCA results you have had. So what you do is you change the weights, and in our case it was 80%. So one criteria becomes 80% more important than the others. And we did it also with -80, and these are the results. On the left-hand side, you can see results with 80% more importance. The red dotted line is the baseline, so that's the line for our that came out of our analysis, so predicted analysis. And to illustrate you what this actually means, we look at maintenance. This is the orange line above, and maintenance in this figure gets 80% more importance, which means that the closer distances, like 2, 4, 6, and 8, score relatively higher, which is logical because when you go, you place the fishing cages closer to shore, the score gets better, and it's better for the maintenance. On the same hand, here on the right hand side, we reduced every importance with minus 80%. Again, the red dotted line represents the baseline, our predicted line. And when we look at fuel consumption, which is the blue graph, if it's reduced by 80%, then the whole graph shifts to the right, which is again logical because when the fuel consumption gets less importance, then the rest of the scores perform better and the distance is moved further away. Now, what can we learn from these two figures is that in most of the situations, except for the fuel consumption and one other, in every situation, 8 kilometers is always the peak of each graph in both graphs. So we can conclude that indeed 8 kilometers is a robust and good distance for the long-term success of the fishing cages. Okay, now we know the distance, so 8 kilometers. I would like to give the word to Chris for talking about the environmental conditions. Thank you.
Thank you, Jetse. So now we'll go on to the environmental conditions. So what this means is what forces is our design subjected to? And to make our focus a little bit more, not so broad, we are only focusing on storms. So what are the storm conditions for our design? So we know our location, and we know we want to focus on storms. So what we're gonna look into is what are the wave height and the wave period for these extreme conditions? What is the current over depth for these extreme conditions? But also very important, where do they both come from? Before we get into the conditions, let's look at the data. So the data we used is firstly local data through ADCP, about 12 kilometers offshore. And we used the waves and the currents. What we also used, because it had a broader range, so I think 40 years, we used ERA 5 reanalysis data for the waves, which has about 40 kilometers offshore for the location. Now looking at the waves, we used the ERA 5 data because it had a broader range. So 40 years, and what we did is we set a threshold and looked at every storm that was independent above this threshold. So what storms had a wave height more than 2.7, and were these waves 4 days apart to make certain that they were independent. With this, we fitted them to a generalized Pareto distribution. This is used to fit the end of tails, so extreme values. And with this, we could calculate the return period. We needed a return period because we had a design life of 20 years, and we wanted to know what wave height is our cage going to be subjected to in this 20 years. So using the return period of 20 years, we came to a wave height of 4.19 meters. But because we used the ERA 5 data, it was 40 kilometers away and was not as close to the shore as our cage will be. So by scaling, by using the local data and calculating a scaling factor, we could actually calculate it for closer to the shore and came with a design value of 3.4 meters. With this 3.4 meters, we calculated the wave period. So what we used the ERA 5 data again, because it had a strong correlation between wave period and wave height. And with a power law regression, we could calculate for every wave height and for our wave height of 3.4 meters, the wave period. And because we wanted to have these extreme forces, on our design, on our cage, we wanted to look at the top level. So what is the confidence interval for 95%? What is the most significant wave period? And we came to 9.34 seconds. Then we'll continue with currents. We had the current data from about 1 meters below the surface to about 8, but we wanted to have more data on top. So what forces or what current forces is our cage subjected to? So we extrapolated the data we had below to calculate the data on top with a third-degree polynomial. With all this data, we use the 95 percentile to calculate the design value. This because not at the wave we had 40 years, so we could do an extreme value analysis, but we had 10 years. So extreme value wasn't going to be, wasn't going to have the same results. So with the 95 percentile, you have a value that is higher than 95% of all the values, but leaving out the 5% that may be due to errors, uncertainty. So it's actually quite a safe value without being too conservative for the structure, because you'll get values that are way higher and are actually not going to be here. And what we figured is that the maximum was 0.5 meters per second at 0.5 meters below the surface. Now for the direction. If you look on top, you can see both for the local and the Era 5 data, you can see that the general direction is from the northeast. But because we wanted to know these storm values, so where does the storm come from, we're going to look at the one below. So this is the top 5%, and you can see a shift from the northeast for the local data to the northwest west. There is a difference. And with the current, if you look at the top, there's a lot of variability. And this is because it's close to the surface, it is more prone to error, and you have winds. So there are a lot of reasons to that this is unreliable. So what we used is a more for depth for the direction. And with this, and again by using the top 5%, we could look up, okay, if we take the top 5% of both the current and the waves, so all the times that they're all on top, so this means all our storms that we're looking into, what is the general direction? And you see that for the waves, it's actually always from the same direction, is about just slightly but with current there are two directions. You have the 250 degrees, which is like, and but again, because the highest force divided for a different, a minimal distance, a minimal degrees between our two forces, so it would actually have the highest force on our structure. So we decided to use the 70. To conclude, for the wave, hey. Was to
just as the Celestine cage, and we subjected the current and wave directions to the same direction to see what the maximum consequence will be. But the only thing we changed was the diameter and the depth. We find the best diameter depth ratio. The concept 1B is the same as the Celestine. The 1A got a greater depth and a smaller diameter, and 1C a larger diameter and a shallower depth. Well, what are the results then? The results looked like this. So over here, you can see all the mooring line tensions, the 9 mooring lines, because there are 3 sub-concepts, of course. And over here, after going to a more steady state, we found out that the 1B, the actual diameter depth ratio of Celestine, actually reduces the drag and has the least mooring line tensions in it. So yeah, that's interesting. So now we know what the diameter depth ratio we're going to look at is. And we made another concept, the concept 2. This is a more simplified structure that reduces material costs and installation complexity because it has 4 mooring lines, anchor systems. And this distributes the forces into, well, looking at 3 mooring lines, of course. So this is the second concept we found. And there's a connection piece between them, just like the ones in Celestine. And our third concept actually looks really like the one in Celestine. This is a 3 cages concept with the same dimensions, just like you saw in the simulation earlier. Well, now we know what kind of design we want, what kind of mooring lines, and what kind of environmental conditions works on it. So now we're just interested into the orientation. So.
Yes, thank you, Martin. So now we know which 3 concepts we want to use. We decided it's interesting to look into in which orientations these concepts experience the lowest maximum mooring line tensions in the most frequent environmental conditions for Sisal. So we simulated 6 the mooring lines pointing at 6 different directions for each concept, subjected to the most frequent environmental conditions of Sisal, where you can see the current coming from here and the wave heading from on top. What we found was maximum mooring line tensions for each heading. They can be seen in these box plots where the lowest maximum tensions can be found in these orientations, where the forces are distributed the best in between each mooring line. Also found the worst orientation where the maximum mooring line forces were the highest. We used this orientation to look further into and did a more extensive simulation for a longer period and a smaller simulation intersection period, and look into the steady state. After the steady state response has been reached, what are the maximum tensions? These tensions we used for our anchor design. So we see the max mooring tensions, and after we knew them, we applied a safety factor, and we came up to design mooring force for each concept in combination with the mooring line angle. On the right, we can see a simplified picture of our deadweight anchor with the mooring line force coming from here and the angle pointing in the right direction. And that way we could make a rectangular concrete anchor sitting on top of sandy soil and apply the ultimate limit state tests by first doing a preliminary design for the first dimensions. Then we did a geotechnical capacity check, so to make sure it could withstand the interaction with the soil, so prevent sliding and being lifted up. And we also did a structural capacity test to make sure the concrete is strong enough to withstand the mooring line forces. So we found the following results: maximum weights, anchor weights of 5.9, 4.5, and 8.8 tons, and the dimensions underneath. And all in all, this made the total recommendations of our research into these different fields of placing aquaculture in Sisal at 8 kilometers offshore at a 9.5 kilometer depth. They have to be resistant against a design wave height of 3.4 meters, a wave period of 9.3 seconds, and resistant against a step current profile of 0.25 with a mean of 0.25 meters per second. We found an optimal depth to diameter ratio of 12 to 4.7 meters and orientations of 350, 70, and 50 degrees. Of course, this was just a preliminary design, so there are a lot of things we think are very interesting to look into for the future. To start with, safety, so to prevent the cages from being emptied unintentionally or vandalism by local fishers or other people. Further research into that is very, very helpful. Also, the costs to know exactly what are the investments of aquaculture and who's going to pay for it needs more investigation as well. Then to determine more precise environmental conditions, additional measurements will be very helpful at different locations to decide to which forces the cages will be subjected. For the design, we only did a strength analysis right now, and for long-term feasibility of the project, a fatigue analysis has to be done as well to make sure the system is resistant to fatigue loading. And also we have only looked into mooring line tensions, and all the other components of the cages were assumed strong enough, but of course it has to be researched as well. And we think there can be a lot of improvements when looking into different mooring line lengths and pretensions, because we assumed one length with one certain pretension now, and maybe the mooring forces can be reduced a lot by doing more research into that. And to end with, investigating the reusing the washed up cages in front of the UNAM site can be a very interesting opportunity to realize economically feasible and long-term successful aquaculture here in Sisal. Thank you all for listening, and we're looking forward for your questions.
I don't know if we should start for the questions from online, or What do you prefer? Okay, if there is time to the talk.
Well, thank you very much for your presentation. It was really interesting, all the results you got, and very useful for the community as well. And I was actually wanting to ask you about this next work. Do you have any idea how far from your optimal design are these cages in front of campus? I mean, in terms of dimension.
You mean the cages that are on the beach
Yes.
over there? Well, they are quite a lot bigger than the cages we think are suitable to use here. So we think maybe reducing them in diameter will allow them to be installed and maintained by the available resources here. But they look very strong, but we haven't really looked into them in very much detail. But
I think those cages in front, those are industrial cages, like I mentioned, and they have to be towed out with like quite big boats. And the reason because we spoke to the engineer who designed the cages in Seminarios, is the reason they chose for the 3-cage setup is to like have a certain amount of modularity, which allows the local fishermen to maintain and maybe move the cages with their own fishing boats. Therefore, they're kind of like an increased autonomy. So I think that's why we also chose Seminarios, because, well, we've seen very similar boats in the harbor here as well. So I think that's the reason also for the 3 concepts is if you design modularity, you can easily increase it. So I think that's the main aspect of the cages in front, is that they cannot be maintained themselves by the local fishermen, which is one of the essential criteria.
Thank you.
Hi, I'm more worried about the materials. Did you consider anything about biofouling and the effects of biofouling on the tension of the moorings? Or what do you suggest to use? What are the best materials to use in these cases to avoid biofouling to prevent the ropes from breaking easily, very fast?
First of all, we didn't really looked into that. We just looked at the tensions, and based on that, we made an anchor dimension. But for the mooring lines, we of course looked at Seminarios and looked at the mooring lines and the connections there. And we mentioned that is like a critical part of that it looked for us like a critical part of their design, because those lines didn't look very suitable for a long-term marine environment. So which materials are best to use? We haven't looked into that, but we think suitable for a marine environment. Those materials have to be tested and certified to do that.
Well, thank you guys for your presentation. I think it's a very good job you've done. I really like it. And I was wondering, I got a little bit lost. Like, so you proposed 3 designs, right? So, or this one that is better than the other 2, or you maybe we can test the 3. I think I got lost a little bit.
So what we did, we wanted, because there isn't just one design that'll work, because it all depends on what capacity do you want to have. So what we try to do is design for modularity. So if you want the volume of 1, then we have the recommendations for just 1 ring. Do you want to change it to 2 or start with 2? Then we have the recommendations for 2, and the same is for 3. So by designing for modularity, we're trying to design for something that we don't know, which is what is the perfect capacity, or what is the not perfect, what is the capacity that people want.
Okay. So do you think it will be interesting or maybe possible to make like some models and test it in the wave channel, or it's just wordless, or I don't know, just to see maybe the tensions and how
Yeah,
these
for
songs.
I think it could work, but yeah, I don't know how difficult it is to make the models exactly like, or make the drag exactly like it would be.
Exactly like
Yeah, and then looking at tension, for sure you can use it. If the drag seems very similar, then yeah, for sure you can use it. And it would be interesting, I think, because you can test it.
Yeah, also most important, we saw that the wave has the most influence. So I think it should be okay. But I mean, over there, you don't really have a current from the other side. So it should be possible though. The most of the drag force, the most of the forces acting on the mooring lines are actually waves. So I think so.
I think one last question is what is exactly what they're thinking to aquaculture, or what's going to be inside the cages? You know that? Like octopus
fish.
or fish?
And we decided to use pompano fish because that's most suitable with, yeah, on Carlos's suggestion, pompano fish, because it can live in captivity and it performs really well in fish cages.
Is the one they're doing in Telestone?
No, in Celestun they use, what was it called? Canane.
Thank you very much. Congratulations. Very interesting and professional. Also, congratulations to Alec. I have a couple of questions. The aquaculture, in this case, in Spanish, is mariculture. Has been private, no? In Celestun, is also private, or is the cooperative?
No, it's a comparative of 56 fishermen from Celestun.
Okay.
And they developed their cages in collaboration with a company.
Okay,
Yeah.
okay. And here in Sisal, there is potential interest?
Yeah, there is potential interest, and that is what we saw at in one of the first meetings we had at the football field here in Sisal. That was about changing knowledge from the fishermen from Celestun towards the fishermen in Sisal. And yeah, you really felt that there was positivity around this idea.
Okay.
But also some skepticism because of the cages, the previous cages, industrial cages, which did not work.
Yeah.
So but you felt that there was more and more positivity about the idea of the fishing cages.
Okay, nice. Did you perform a cost analysis, because the investment is quite large for a small cooperative of fishermen, right?
Yes, of course. That's one of the points that future research is needed. But also, we tried getting the exact cost. We know what the total cost of the Celestun cage was, but those are not the real costs due to various reasons. And we tried to get the cost for the materials and the nets, which unfortunately we couldn't obtain, or didn't have enough time to obtain them. But the reason we took Celestun as a basis is because we knew it was economically viable for such a small fishing community.
Yeah.
So I think we all sat around like, okay, how are we going to start? Like, are we going to start with those cages in front? Like, I mean, that's not handy because it's not economically viable. We know that, so we have to design a whole new cage. We thought it was better to know a cage works in a community like this one, and then adapt it to the Sisal conditions.
Great. And the Celestun cages are actually working well?
Yeah, right now they are for the hurricane season, they are taking out the nets. So they're not using them for, I think from July to December. But in December they will put the nets back and the fish, and they are in operation. Yeah.
Okay. And one last one, very quick. This wave design of 9 seconds period and 3.5 meters, is that acceptable for the fish inside? Or we don't know?
I'd say yes, but then I'd be guessing. No, yeah, I think, yeah, we think so. If it works in Celestun, but we don't know for sure. Actually, my focus was not on the fish, but was on the cages.
Oh yeah,
Yeah,
the nets
thank
are
you.
also taking out at the hurricane season, so there's no really fishing activity.
Oh, I
Still.
see.
I think we found some sources that are also in our report that I think waves are not the big problem. I think current is, because if there's a lot of current, the fish have to use a lot of energy to kind of stay in their place. So it's more the current, and the current, like the maximum current is still, according to literature, is still okay for the fishes.
Okay, thank you. Thank you very much.
Thank you very much for this information. It's very, very useful for us, for the project, and for the people. And I can understand very well how do you find that the values of the waves and currents and many things that you showed. But certainly you know, and they are true, I suppose. Certainly the aquaculture here in Sisal is a challenge. Everybody here. And the cages is the hope for many of many people here, no? Because the fisheries is getting down now, and the people is waiting for a miracle. and we are living in a season or in an age of warming that is affecting the fisheries and the population also, the fisher population here. Then, in your opinion, what kind of experiments should be done in the future? Because obviously those designs are very nice, but we don't have enough money to make to place some cages in the sea. The cost now, the actual cost of the one cage is around 1 million pesos. That sound not much money for the budgets at the government level, but just sound as a very high much money for the people. We are pushing to obtain the support, but in the meantime, we pretend to make a lot of experiments with the people here with the waves channel. But in your opinion, what kind of experiments? Because I am thinking in the prototype, not in that cages that are in the beach. What kind of prototypes, experiments do you want, or you like, or you hope to do? What do you think about that?
So I think there are multiple aspects. The social part and actually, yeah, the testing. So as Tom said, we now know the anchor weights and the right direction. What we don't know is what diameter the ropes have to be, for instance. The tubing, what should it be? What netting should there be used? So all the different components have to be tested in the same way that we did the anchor. And maybe also we now only did an extreme value. So what happens when there's one or multiple waves in a storm and it hits them? But what happens when it goes years and years and years with mean values? So also fatigue analysis should be done.
Yes, I think that's the technical part. So I think what we've designed the anchor for is like the biggest waves, most current, like the heaviest tensions. So we know those are the maximum tensions that are going to happen in the whole 20 years. But I think more about the social aspect is first to, overcome the skepticism of the community first, because you are growing the pompano fish in the lab, right? So my recommendation is that first show in a smaller scale, so you don't need heavy anchors, you don't need big cage. In a smaller scale, show that it works, that you get good yield from fishing in a very small cage. And if you know, if you get the community on your side and you show that it works, then you can start thinking about how are you gonna expand. And then you need the dimensions and all the conditions of a cage to expand. And you would know them if research has been done. So you don't need, I think the testing, of course, testing is expensive. But yeah, we've done a data analysis on the heaviest conditions. So it should be way more than there is going to happen basically in CISO. That would be my.
We have 2 years to make the experiments. I hope. No, thank you.
Do you have any idea about how much these farms can actually produce compared to regular fishing that is happening now? Maybe it's not part of your research, but can you compare maybe to Calistoen, or do you have an idea?
We don't know the exact numbers because it's very, we don't like you have the local fishing price per kilo, and so there's a lot of variables. But I know that when we had our talk with the Calistoen fishermen, they do export a lot of fish that they generate from the farms. But I don't know. I think we kind of got the number from the engineer vaguely, but I can't remember now.
But you do know it's economically valuable, right, in Calistoen? So okay.
Yeah, we do know that because the Calistoen cages they've proven that, and also that's why we included the tourism part, is because they think, and we also see the big building built here of apartments, that tourism is going to increase here a lot, whether people like it or not. But and then the tours are a big part, or can form a big income for the local community, which improves their livelihood as well.
Thanks.
Well, congratulations for the nice work. And I just want to ask you if you can tell about your experience, because no one of you are a Spanish speaker, right? So I mean, how do you deal with these interviews that give you the weight, that give you the location? I mean, in terms of the language barrier, I mean, that will be my
technology.
No, Sebastian helped us quite a bit with the Spanish, even as it's the best of us, actually. But we recorded it and we used an AI tool to translate it. And then, we can, it works pretty good. So, but the informal talking, and even David, he helped us one time to get an interview. So we managed mainly through AI tool to translate it. We loved it. Yeah, we loved it. Yeah, no, I think I speak for all of
your experience here in CISAL, please, because for us and for our students, it's very important to know, because you are foreigners. But many of students here are foreigners also, coming from different parts of Mexico, and they have the same or similar experience beyond the language. Many times I can understand the people here also. Then talk about that. I think could be very important, the human part of your experience.
No, we really liked, we really loved CISAL actually, and quietness and the beautiful beach. We're not used to that in Europe. There are all big towers and hotels and stuff like that. So we really liked it. And in the weekends, we like to travel around to see the area of Yucatan a bit. So that was also very,
see more busy places and Chichen Itza and stuff like that. So that was also very, yeah, we loved it, the whole experience, the whole 2 months. I think I speak for all of us, yeah, when it was one of our best journeys we had so far. So yeah, we really loved our 2 months here.
And there were, of course, some ups and downs in living in such a small village, I need to say. Oh, big up is, of course, the beach and the beautiful place and the quietness, of course, just as Jetse said. But yeah, I mean, sometimes you don't have any internet. There's a tropical storm coming by. No electricity. Yeah, that's... but overall, it's a nice experience. The people over here are very friendly, and well, it's becoming a tourist place, and I guess I know why, because it's an amazing place. Oh yeah, yeah, and the big one, we didn't know what the market was. There's only one place in Holsisel where you can actually buy vegetables, and that was like after 3 or 2 weeks, we just there's a market over here, and we didn't know that, and now we do.
Yeah, in terms of tension, I understood that the Celestun design was the best.
The depth to diameter ratio they used in Celestun was the one we, when after simulating, found out was at the lowest drag. Yeah.
Yeah, and is that a coincidence, or there was some design for those cages? You don't know.
Yeah, they had did a lot of research into it as well, and they were really made by a company who makes industrial cages as well. So it's not that they did it by themselves or without any research. No. No. And what maybe is interesting to add is that they told us they used 10 tons for their anchors. We found for the 3-cage setup, we found 8.8 tons. So that looks a bit less. So they must be safe, but they use sand anchors, of course, and we simulated concrete anchors. So yeah, exactly. Yeah.
Great. Well, thank you for the presentation, and we will move with the next team.